Okay. It's a great pleasure to introduce Elias Kammoun. I met Elias many years ago in Lebanon, where he was studying in Beirut. He got his bachelor's and master's degree from Saint Joseph University in Beirut. And then he moved to Italy, Trieste, where he did his PhD. After his PhD, he crossed the Atlantic, went to Ann Arbor, worked with John Miller's group there for a few years before returning back to Toulouse, where he joined the XIFO team of the new Athena mission, who will come at some point. And then a couple months ago, he moved to Roma Tre, the University in Rome, where he's currently working there with colleagues. Elias is working on AGN, variability studies of AGN, spectroscopic studies of AGN, and he's going to present work that he did last few years, right? Yeah, last few years together. So, Elias, please go ahead.
Thank you, so it's a great pleasure to be here, to be back here actually. So I visited 5-6 years ago, and now it's always good to come back. So yeah, this is a work that we've been working on with Cephis, with Michal Dovchak from Prague, and with Christos Panayiotou from MIT, about how we can probe the interaction between the X-ray corona and AGN and their accretion disks. So just a brief introduction about what AGN are, how they function, what's happening. So we believe that in most, it's not in all galaxies, we have a supermassive black hole at their very inner center. By supermassive, I mean a few million to a few billion or even more solar masses. And in a part of their life, these black holes have accretion episodes, so they become what we call active. That's why they are active galactic nuclei. So they become active by accreting matter through an accretion disk. And the AGN is what we call AGN is a bit a mess by using all the definitions. So what we believe now is that more or less most of them are kind of the same, or similar, very similar, having the same components, but we change classifications, we change properties of the AGN by looking at different angles for these ones. So the different parts of AGN are the black hole, the accretion disk. Then if we go a bit further out, we have what's called the broadline region. So these are kind of cloud, these are gas that's orbiting very fast, and thus broadening the emission lines that we get. So that's why they are broadline regions. If we go a bit further out, we have the narrow line region. So these are further out regions, so they are slower. And we believe that there's most likely some torus-like material that is very far, that is cold, that is dusty. And in some of the AGN, we can see some relativistic jet. In most of them, we don't see the relativistic jet. So due to this, we have that the AGN is contributing to the full electromagnetic spectrum, going from radio up to the hard, the gamma rays here. It depends on whether there's a jet or no. It depends on how we are looking at those, so we can or we cannot see one of the components. Obviously, we didn't mention the X-rays yet, but if we zoom in at this part, we see that in the very inner part of the disk, we have of the AGN, we have the accretion disk, and we have some region emitting in X-rays, what we call the corona. So it's a hot relativistic medium of electrons that's emitting in X-rays. We still don't know how these electrons got there, how they are powered, what's their nature, but we know they are there. They should be there because we see the X-rays. So in my talk, I'll be focusing mainly on that very inner region of the AGN. So as I mentioned before, we can look at AGN in different wavelengths, and each wavelength will tell us more about the part that's contributing mainly to that wave. So you know that with the EHT, the Event Horizon Telescope, we can have a picture of an AGN, or actually of two black holes practically. But then it's very time consuming, it's very hard. So we cannot get a real picture of these regions. No, we cannot get an image of the accretion disk, an image of the corona, etc. It's very hard. However, what we can do is use reverberation techniques. So we can map these regions and try to get their structure, where they are, how they are distributed. So if we have, it's a kind of a simple technique practically, not very simple in practice, but if you think about it, it's very intuitive. If we have some part of the disk of the AGN that is variable, that's emitting light and it's variable, the light is propagating, the light will reach another region where this light will be reprocessed and re-emitted. So if we look at the light curve in one band and in another, and then we try to cross-correlate them, we can see that there may be some delay due to the light going to that region, being reprocessed and coming back to us. So that's what we call, it's like an echo. So that's why it's called reverberation mapping. So by mapping, we can map, by variability studies, we can map the different regions. If we look in X-rays, for example, we look at variabilities and time delays of the order of hundreds of light seconds. So we are mapping the very inner part of the accretion disk that's variable. So we are at the terms of gravitational radii. If we look in the UV optical continuum reverberation in that band, just looking at the continuum, then we are at a time scale of few light days of interaction. And we are probing, we know we are probing the accretion disk then. If we look in the reverberation of the UV optical broad emission lines, now we probe the broad line region, which is at the order of light weeks away from the center. And if we go to the infrared, then we are probing dusty emission. So we are probing the torus at time scale of few months to few light years. So there is a very nice review by Kakat, Bentz, and Kara that summarizes all these techniques and states what's now the situation in the field. In my talk, I'll be focusing on the UV optical continuum reverberation, so how we can use that to probe the accretion disk. So what do we see practically when we observe an AGN in UV and X-rays? So we have the accretion disk. The accretion disk is emitting a thermal emission. So if we think about, if we divide the accretion disk into annuli, so we take an annulus, this annulus is emitting a thermal emission, so a black body-like emission. And then it depends on the temperature, so we have different annuli, so we have different black bodies, and then the sum of this, it's a multi-temperature black body emission that's characterizing the accretion disk. For supermassive black holes, the bulk of the emission is practically in the UV optical range. If we go to much smaller black holes, the disk emission will go into the soft X-rays. But now, for our purposes, we are in the UV optical range. So this emission, we will see part of it, but also this emission will go and it will interact with the X-ray corona and it will cool it off. The corona is hot electrons, so they will inverse Comptonize this emission. So they will bring it from the optical UV into the X-rays. And the emission, the spectrum in the X-rays is practically characterized. It's inverse Compton. It's characterized by a kind of a power law shape and the high energy cutoff that is telling us what's the temperature of these electrons, and a low energy cutoff that is due to how much we are injecting photons from the disk into this region. So we get now what's called the direct emission or the primary emission from the corona. But that's not the full story, because the corona is emitting in all directions. It's isotropic, so we will get part of these photons, we will see part of those. But in return, the corona will irradiate back the accretion disk. So there will be always an interaction, kind of a feedback, like going up and down. And then the corona, the X-rays will irradiate the accretion disk. And what we get then, what's called the reprocessed emission from the accretion disk in the X-ray, what we call the reflection emission, the reflection spectrum for AGN. And then that's characterized, this is the blue spectrum here. So we have the red, it's the continuum, the power law, and then in the blue, we have the reflection that's characterized by soft X-ray lines, practically, and the iron K alpha at around 6.4 keV line, and what we call the Compton hump. So this is the hard X-ray emission. So this is what we call the relativistic reflection. And it can be used to probe the disk, to understand the structure of the disk, the irradiation pattern from the corona to the disk, so where the corona is located. And also it's commonly used to determine also the spin of the black hole, because this will affect the broadening of the line, and then from that we can get the spin of the black hole, how fast the black holes are spinning. So this is what we think, and this is what we see. We have very strong evidence of irradiation of the accretion disk in X-rays. So if we look at the spectra of AGN, we can see that we have signatures of broad iron lines, and we have the Compton hump that we've been talking about in spectroscopy. And if we look in time lags, we can also see that the disk is responding to the corona. So the emission from the disk is coming after the emission from the corona. And if we see the time lags as a function of energy, we see that it has kind of a similar pattern to the spectra. So we can see also that there's a lag that's mainly in the iron line, there's soft lag. So we have strong evidence from X-rays that actually the corona do irradiate the accretion disk and we have the reflection. If that's the case, so naturally speaking, since not all of the emission from the X-rays will go back into reflection, so the disk is absorbing, we know that the disk is absorbing some part of that. So if the X-rays are eliminating the disk, we should expect then the X-ray and UV optical to be correlated, to see variation in the UV and optical after a certain delay to the X-rays. So is that the case? And then this has been seen. So we can expect to see some correlation, and the correlation between the UV and the X-rays have been seen since the 90s, practically. This is with Ginga, I believe. And then later on, we'll talk about what's the current status. So we can see that the X-rays, we know that the X-rays and the UV are correlated. So there is some interaction in there that could be due to the fact of the thermal reverberation that we talked about later. So this was the status in the 90s, where we have the light curves for monitoring and the X-rays, the UV, and in different lines. And this is the current status. You can appreciate the quality of the data, how it's much better now. This is for the same source, NGC 5548, that we've been talking about. If we look at the light curve, if we take this point here or the peak here, we see that by going into longer wavelengths, this point here, the trough here is shifting towards later time, the peak is shifting, and the emission is getting broader. So this is a clear significance of the lags that are observed. And if we do some cross correlation, you can see that this lag is increasing with wavelength. So what we believe is happening, it's the different scenarios that could be there. It's either due to the elimination we talk about, or maybe if it's due to the changes in the UV are intrinsic to the disk, due to changes in the accretion rate, due to change to some fluctuations. But this cannot happen, because if the accretion rate is changing and the fluctuations are propagating in the disk inwards, then we would have seen the effect reversed. We would see the lags practically increasing as we go to shorter waves. That's what we don't see. So the most plausible explanation is that this is a response to the X-ray variability. So if we have the X-ray source here, it will appear to be flashing. Then after a certain time, the disk will respond to that, giving an echo to that, and then we will see the light. So that's how we see the delays. So there's a huge observational effort that has been put to investigate that, to observe that, using SWIFT, using HST, using ground-based telescopes, and we see that effect in most of the AGN, practically, if not in a large fraction, let's say. So I'm showing here practically that the first intense monitoring of NGC 5548, that was with HST, SWIFT, and ground-based telescopes, and we see the time lag as a function of wavelength. The data points are shown here, and we see that there is a clear increase in the time lag as we go to larger wavelengths. So people try to do simple approximations, just taking the time lag to be the time delay to be the light crossing time. And from that, we can get the temperature of the region. So they associated each region to a certain wavelength, saying that this region is here. Practically, it has this temperature emitting in this wavelength, responsible of this time lag, and so on and so forth. And from that, using a simple Shakura-Sunyaev approximation, you can get that the time lag should be proportional to the mass accretion rate at a certain factor here, a certain power, and to the wavelength to a power of 4/3. If we try to use this simple prescription in order to explain the data, what we see is that practically, we're here. So what we see is that the shape of the observed time lags is consistent with a lambda to the power 4/3. So the shape is consistent, but if we want to fit the amplitude of that time lag, the amplitude is, the expected amplitude is much lower than the observation. So if we want to fit with a normal accretion rate that's expected for this kind of source, in that order of magnitude, you see that this is the line here that is very low compared to the data. And in order to match, we have to go to very high accretion rates that we don't expect these sources to be accreting that high. So this is happening in most of the sources from these campaigns, and the main result, the first main result is that the shape agrees, so this trend is there and it agrees. The amplitude is not, so either the disk is larger, the accretion rate are not the same. There's something missing in the physics that we have. And the second very interesting result, or the third interesting result from these campaigns, is that if we plot here the UV to X-ray maximum correlation coefficient, so the correlation practically, how correlated the UV and the X-rays are, versus how correlated the UV and optical are, we see that the UV and X-ray correlation is always moderate or very low compared to the correlation between the UV and X-rays are less correlated than the UV and optical. This is the unity line, the identity line, and they are always around 0.5, 2, 3. So there is something also missing in our understanding, maybe. And if our model is true, then we expect a larger correlation, or to be that the UV X-ray and the UV optical to be correlated in the same way, but we don't see that, and this is a main question. Is the X-ray variability really the responsible, really the driver of the UV and optical, or there's something else that we are missing? So in my talk, I'll try to answer to these questions. This is a work that we started in 2019, I think, to investigate this problem and to see what's really happening. So this is here. I'll be showing the models that we've been developing to model the time lags. But as you will see, it's not only the time lags. We will go beyond the time lags using a simple model, practically revising the model that I explained, but putting more physics into it, putting all the knowledge that we have accumulated throughout the years from X-ray reflection, from different techniques, etc., using simple and general relativity effects, a fully self-consistent model, and with all the knowledge that has been and the work that has been done and the disk reflection that we have. Well, this is our model again. We assume, for simplicity, that the corona is a point-like source. We know that, in fact, it's not true. It should have a dimension, but this is the simplest way to start investigating, and that's eliminating the accretion disk. So we can know by ray tracing, we know how much photons are incident at the disk, how much the disk will reflect in X-rays, and the difference is what the disk is absorbing. So knowing the absorbed flux, we can know now what's the new temperature of the disk that is due to heating by absorption. So this point had a temperature, then it's heated more by the X-rays, by the absorbed flux, so its temperature increases, and from that, we can track in time how the disk is responding to that X-ray light that is happening. And we can get what we call the response function, so how the disk is responding to the X-ray flash, and we can get ultimately the final observed flux, which is due to the X-ray irradiation. I will focus on the first part of the talk on that disk response, and then we get back to this later. So what we do is that we send a flash of X-ray to the disk, we wait, and we see how the disk is going to respond. Of course, you can set the mass, the accretion rate, the spin, etc., all the properties of the system, and we see that. So we send the X-ray flash at time 0, and then we see the response function. This is what we call the response function in different ways. And from that, we can get the centroid of that response function, which is approximately the mean, the average time lag in that way. So what do we see here? First thing that we saw is that all the responses at all wavelengths start exactly at the same time. So this is, the blue is in UV, the green is in optical. They both start at the same time. And this is natural, this is normal, because if a part of the disk is responding, this part is emitting a thermal radiation. The thermal radiation is in all wavelengths, it's not monochromatic. So we expect that this part of the disk, this region of the disk, to be emitting at all wavelengths at the same time. So we have this, and we see that the width of the response increases as we go from UV to optical to longer wavelength. And this is because the light will reach further out regions that are colder regions, and this will contribute more and more to the longer wavelengths. So here the response drops very fast in the UV because it's mainly the inner hotter regions are contributing to that wavelength. As we go to the longer wavelengths, we have contribution from further out regions, and thus we have the response that is broader, which will lead later on to a larger time delay on average. So this is the picture that we believe is happening. We have the radiation, and each of the disk elements are contributing to all wavelengths, but they start at different times and then reconstructing these responses. So we ran our model for different sets of parameters, and we tried to simplify things and for different mass, height, accretion rate, correction factor, X-ray luminosities, and we got a simple analytic prescription that will allow us to fit the data, because we want to go from the model to fitting the data and see if we can really fit, if we can constrain. We did that for 2 values of black hole spin. And as you can see here, practically this was a set of 7 sources that were monitored. And this model, the simple model, practically works for all of the sources. So what we did is practically, we know the X-ray luminosity because these sources were observed in X-ray. So this is the observed X-ray luminosity. We fix it. We assume a certain color correction factor for the disk. We know the mass of the black hole, we fix it, and then the 2 parameters that are left are the height and the accretion rate, and we fit for those. And in some of the cases, we may be able to get some really strong, some constraints on one or both parameters. In some cases, when the data do not allow us to do it, the constraints are a bit loose. But in any case, what we have here is that the model works. The model can explain the data without the need of strange or very high or very low or whatever accretion rates, without the need of new physics, without the need of having larger disk, etc. The simple model just works in all the sources. So yeah, this is what we've done until 2023, until this year. And then now what we have is practically a newer version of that model, not using the simple analytic approximation, but we wanted to explore more, to have a more flexible model, to have different options. So we have this new code, KYN XLTR, that is practically the same here. Now we have 2 options because we want to investigate how the X-rays are powered. So we have 2 options in that model to see either the corona is powered by the accretion of the black hole from the accretion disk. So the accretion power is transferred somehow. You can use the magic of a magnetic field to transfer it, and then give the electrons of the corona that power, and then see what's happening. Or maybe we are extracting the power from for example, from the black hole itself by a Blandford-Schneiek or a Blandford-Payne or whatever phenomenon that you want to imagine. So we're extracting it not from the accretion disk, but externally, another magic trick that's happening. And we wanted to explore both of these options. So one could use different combinations of parameter. One can choose which parameter to fix, which let free, so giving the user more freedom and more flexibility. And we tested this model with all the complications and all the combinations that we could for 4 sources. And if you remember that there was a problem at the beginning that the time lags were not fit properly. We needed high accretion rates or something weird to happen to fit the data. And that was a problem. But now here, if you look at these, so these are different combinations and almost all of them work, or a large parameter range is working that is reasonable also, that could explain the data in all of these sources. So we are now in a different problem. Before, the models were not working. Now the models are working too well, and we cannot, anything could fit them. And this is another problem because we want to constrain things. We want to understand how things are happening.
But what accretion rates do you find for these bits?
For these, so it depends on the source, but for what we have is practically the expected, we get the expected accretion rate plus or minus a certain uncertainty, a reasonable uncertainty that is, let's say we are at the 10% or lower Eddington. So the accretion rates are consistent with what we expect the accretion rates to be. So the first conclusion from here is that the X-ray illuminated standard accretion disk can easily explain the UV optical continuum time lags, assuming normal accretion rates, and for all of the sources. So now so this is the first part on time lags. Now I will focus more on the work that we've done on NGC 5548, where we could go practically, the data were too good, and allowing us to go into more details, into exploring more what we can extract from this, what we can learn. So the choice of this source is very obvious. This was the first source that was intensely monitored. You can see the monitoring from HSD up to SDSS-Z band for a very long period of time, a few 300, 400 days or so. And then we can try to answer all the questions that we had before, regarding the variability, regarding whether the X-rays are the driving of the variability in the UV and optical, and see what's the source is doing during that monitoring. So this was part of the work that we've done before. So we could practically fit the time lapse in the source and get some constraints on the height and on the accretion rate of that source using only the time. But what we've done later on with Christos practically is to, since we have the responses, we know how the disk is responding, we can practically estimate the power spectra and the different wavelengths, assuming that the X-ray is the driver, and to check whether we can, from that assumption, fit the variability in the UV and optical. So we start from the X-ray power spectrum, and we assume that this is the power spectrum that is driving the variability. And we use our responses to model the variability in the UV and optical, and we find that the model fits very well the observations, fits very well the observed variability. And when we combine all of this with the measurements of the time lag, we can even put more and stronger constraints on the parameters of the source, on the height, and on the accretion rate. So practically, this is the first evidence that we have that despite the fact that the X-ray and UV may seem to be not very well correlated, the X-ray can be the driver of that observed UV optical variability. So we have this result. So we have the time lags that are explained. We have the variability, the power spectra that are explained. And the last bit of the puzzle, the last piece of the puzzle is what the spectrum, the UV and optical spectra, the variability, the spectral variability, and the energetics. So in 2022, in the paper led by Mikhail Dovchak, we have a new model, a new SED spectral energy distribution model, KINSAD, that could, within that framework of X-ray irradiation, could tell us what's the expected SED. So here, something that one has to be careful when dealing with SEDs and variability in SEDs, because I'll not go into the details of the equation, but practically, if we want to intuitively think about it, if we have the disk responses here in two wavelengths, so you can see that at short wavelength, the response goes up to 1.5 days. But in the I band, for example, at longer wavelength, the response can extend up to 10 days or even more, depending, of course, on the parameters. But more or less, we are in that situation. So if we are observing in the I band, let's say today, the flux that we are getting in this wavelength is not responding to the X-ray flux of today, but it's responding to what the X-rays were doing a few days ago. So if we want to fit simultaneously the X-rays from today and the optical UV from today, we are fitting two different things because the source is not consistent anymore. We are observing something responding to what happened a few days ago with what's happening today and what will dictate the variability in the coming days. So this is a tricky thing to do. So there are two solutions practically. Either we observe the source for a very long time, and then we take the average, and we say that this is more or less the average state of the source. That's fine, but it should be very long, you know. Or what we can do is construct step by step a time-resolved SED by taking a certain point in time here, and then integrating back in X-rays to see what the source was doing before today, and say that this is the average state of X-rays, and this is our UV point here that should practically correspond to that point backward in time. So we started with the easiest time average spectrum. And from the time lags, practically the best fit time lags were for a spin 0, a spin 0.7, a spin of a maximal spin, and different powers transferred to the X-ray corona. And by plotting, I'm plotting here all the configurations from there, and practically in the time lags, and practically you cannot discern what is what or what's fitting better than the other, because more or less all of them have the same quality of the fit. So what should we do? We need to discriminate. We need to rule out models. We need to favor something. Is it maximally spinning? Is it moderately spinning? What's happening? So we fitted the time average spectra, starting from the configuration that we had before for the time lapse. And we got the result that a maximally spinning black hole does not work. Whatever we do, it cannot work at all. So the only two cases that survived practically are the spin 0 and spin 0.7. So this is a first interesting result to have. But then we asked ourselves, could we do better? Can we go further? So what we did here is we were very brave to try to construct time variable SEDs and try to fit them. So we took a point in time in the UV practically, and we know that for this wavelength, the response should be more or less of the order of 1 to 2 days, a bit less than 2 days. So what we did is that we fixed a point in UV, point in time for the UV, and then we integrate here the X-ray light curve, here's the UV light curves, and we integrate back in time starting from this point up to 1.5 more or less days backward. And we say that this is the average X-ray spectrum, and this is the UV, and we fit those now together, and then those, and then those. So we constructed 15 time average SEDs, and we fit them, and surprisingly, we can fit. That's a good thing. These are the 15 SEDs that we fit with an accuracy that's within few 10% or less. The X-rays are noisy, and the UV optical we are at 2-3% accuracy, and only one spin survived. We had 2 spins before, we had the 0 and 0.7. Now only one spin survives, which is the spin 0, and that could give us a very good fit. So what's the reason of the, and then before jumping to that, so what we do here is compare the same figure as before. We compare the observations, practically, the black points here, the average ones, and our model prediction of the flux, and we can practically fit very well the variability. So these were, if we cross-correlate those two, practically we'll have a low correlation, but assuming a model that where the X-rays are the drivers, we can reproduce the non-correlation or the weak correlation, which is a very important thing to do, because the physics that we assume is that the X-rays are the drivers, the X-rays and the UV are correlated, and we go to the observation and we see that even though the physics tell us that they are correlated, what we observe is a weaker correlation than what the physics is doing, how the two parts are connected. And another important thing here is that for all these 15 spectra that we fitted, we assume the same accretion rate. And then the other important conclusion from that is that even if the accretion rate is assumed to be constant, so the disk intrinsically is not varying, and all the variability is then due to the X-ray illumination. And that's also a very important thing to note, because we don't assume that the disk is changing. We assume that everything that is observed is due to the X-ray illumination, and still we can fit perfectly. So here are the parameters, the 3 parameters that we had: the height, the slope of the spectrum, and the power transfer to the corona. And practically, the combination of these changes is what's giving us the observed variability. So each of them separately, if it was each of them that is variable, it would dictate a certain pattern in the variability. But then the combination of all 3 together is what's giving us this moderate variability that is observed, and not a very strong one. So if the height is getting higher, the other gamma is getting lower, for example, I'm just saying anything, then the flux that is observed will be changing accordingly. And that, yes.
What is the height?
The height is the H is the height of the corona, the position of the X-ray corona, since we assume a lamppost. So these are the conclusions that we got from all these works that we had so far. So the X-ray UV optical time lags in many sources are well fitted using this model. It's a model, again, that does not assume any new physics. It's just revisiting the same model, but doing the calculations self-consistently and tracking everything properly. The second conclusion is that the UV optical power spectra, so the variability in NGC 5548, can be explained very well. The time average X-ray UV optical SED can be explained well. The time variable SED can be explained well. And also this model, another paper by Christos here, using this elimination, you could, he was running a lot of simulations to show that the moderate correlation practically between X-rays and UV could be reproduced using our model, just as I said, due to the combination of the parameters that are variable. Then there is a very recent work that's submitted by Marius, showing that the UV optical variability in many sources, not only in NGC 5548, could also be well fitted using our model. And in a paper led by Joseph last year, I don't have the time to go through all the details here, but also there was a similar problem in lensed quasars, that people thought that the quasars are much larger than we thought they are. So by introducing the X-ray irradiation, we can explain the size, the observed size of these lensed quasars without the need of anything extra. But that's not all, because now what we're trying to do, and these are my last 2 slides practically, is that since we explained the correlations, There are a few sources that do not show any correlation at all. It's not just a weak correlation, it's really no correlation at all. So there's Iris 1322.4, 1H0707, Markarian 1044. If we look at the correlation at the X-ray versus UV, we see practically no correlation. So what's happening? If we look at these sources, if we look at the spectral properties of these sources, we realize that these sources have very strong reflection features. The reflection is very strong there. You can see the iron line in the K and the L band, the L shell. Even here, you can see the soft excess here. So what we're trying to investigate is whether how the reflection and the thermal reverberation are correlated practically. And this is a very preliminary result. We're still at the beginning of that work. So practically here, what I'm showing is that this is for spin zero, this is for maximum spinning. I'm showing the fraction of thermal reverberation that's expected from the model over the total fraction here in the shaded area. This is where we observe the thermal reverberation. This is the X-ray region. So here, practically, this ratio corresponds to how much the reflection is contributing to the total flux. And the color bar is the height going from blue to the low height up to very high heights. And then you see that as we go from blue to red here in the thermal reverberation, so as we increase the height, the thermal reverberation in our band here, in our band that we are interested in, goes larger. And instead, the reflection goes lower as we go to larger height. So similar thing, even stronger, is happening here in the highly spinning black hole. The effects are stronger. So practically for these sources that I showed before, these sources are expected to have very high reflection. So they are the blue sources here. And for these blue sources, we expect the thermal reverberation to be around 10% or even less of the total flux. So even if thermal reverberation is there, it's just 10% of the observed flux that is changing, and then it will be very, very hard to detect these changes in this source. And that could be then the explanation of why we don't observe any UV and X-ray correlation in these sources. So my last conclusion slide is that practically the model works, explains the correlations. Now we'll try to see if the model explains the non-correlation that we are seeing, because for a model to be viable, practically it should explain all the observational aspects that you are having, or most of them, or to know where's the limit of the model if the model is not, because none of the models are perfect. And then this is a new kind of window, if you want, or a new tunnel or a new path to match now the thermal reverberation, the UV optical, and the X-ray reflection as they are probing the same regions. They are probing the same physics, but using different tools. And how we can now, we want to see how we can construct a complete picture of the HN variability and the HN behavior. And thank you.
Yes, please.
Yes, thank you very much. When you build your model, you assume that the X-ray from the Z is like 0.5.
That's true.
Have you tried to make a different assumption with dimensions to see if the model changes? I don't know, is it possible?
We didn't start yet. I mean, we have the idea, but it will be much more complicated because then you will need a 3D model, which exists practically. There is different codes that treats the corona as a 3D, in 3D. One of them is Monk, developed by Wenda Zhang. But then to have a completely consistent model where you have the photons from the disk going to that 3D corona, giving it back and introducing all the GR effects, it gets a bit more complicated. We have that in the back of our mind. We're still trying to explore the toy model, if you wish, that we have now and try to see how we go further. We did some tests practically exploring just a spherical corona, like a ball, a 3D corona, just in terms of spectral shape and spectral power and the power, the energetics. And we are consistent, the point-like source is consistent with a spherical blob practically within 10–20% more or less. So we are not that far, but then you want to explore different geometries elongated along the axis or radial, then it becomes more complicated to deal with that. But we may try to do it in the future, but now we're still, we didn't reach that step.
And given that this one model explains when the data, I presume that we wouldn't expect large differences.
We should not practically expect very large distances. Now, we know the corona is compact from different observational properties of what we're seeing. The corona should be compact. So it cannot be a corona extended to a very large regions. But what's the exact shape and how much different it will be, we cannot tell.
Yes, is it possible that part of the X-ray flux or the X-ray spectra is contributed by a reflection from torus?
That's true. No, we know. I mean, we see that, for example, in the X-rays, we see that there are broad iron lines and very narrow iron lines that we expect them coming from the torus. But then the amount of flux that we are getting from the torus compared to the primary and the disk reflection is low. You know, it's first the torus is neutral, so you don't. So here, for example, we go back to the intro. Yes. So this is the reflection from the disk. If you want to mimic a reflection from the torus, the features will be narrower, and then you will not get much flux in the soft. So it will go steeper down, and it will be at a lower flux level because the amount of X-ray, the primary that are reaching the torus, are much less than the X-ray that are reaching the disk. You know, as you go to larger angles, it gets less and less flux that will reach the further out regions, and especially if the corona is very close, you have also the relativistic effects that will concentrate, the light bending will concentrate the X-rays in the innermost part. So they are there, we see them in some of the sources, obviously, but they cannot contribute to the bulk of the emission.
I was wondering how you mentioned about the color term and
Yes.
how important it is. I was wondering how consistent are the results from your SED fitting, from which you can infer a color term, with the measurements of the color term from your variability?
They are the same practically.
Okay.
So we use. So when to go through it, we started from these here. Oops. So we started from these. Now we fixed the configuration. The color is 1.7, let's say, and we try to fit the SED with a color correction of 1.7, and we see if it works or not. And for the average, the only survivors are the spin 0 F-call of 1.7 and spin 0.7 and color correction of 1.7. Then for the variability, for the variable SED, it was the spin 0 and F-call 1.7. So we are always consistent in the parameter space between the variability and the time lags and the SEDs.
So in the SED model, there is a color term.
Yes.
And
it is the same as the time lag color term that we have.
Okay, but then isn't this a circular argument?
Sorry?
Isn't this a circular argument?
In which sense?
In the sense that you measure the color term in one way and you fix it here in the SED fitting, and then you say, okay, but the color term is consistent.
Yes, but otherwise, you know, I mean, we can let it free if you want, but then it will be too much degenerate with the other parameters. Yes. It's time lags. It's a different. It's a different data set.
Okay.
And you force them to be the same.
Because I was thinking that the SED is actually an SED fit where you have the disk black body with all the modifications and so on. And then by comparing that with a simple disk black body, you calculate what is the color term.
Yeah, but
Yes.
if it was different, you wouldn't be able to.
Okay,
explain.
Yes,
You would have different.
different things.
You can't fit with different forms. But then you will not be able to explain the timeline. These can be fitted with a different form. But
But-
then
but,
how can you explain the timeline?
Okay.
It's the same source, same data.
Yeah, same data set practically. It's the time lag, and here this is the SED. So the same period, everything is the same.